The primary purpose of the X-ray telescope, XRT, is to make pictures of the Sun using the X-rays radiating from the Sun. The XRT can also make solar pictures with visible light. This diagram shows the basic parts of the XRT. We will describe how each part works to form images of the Sun. When the XRT is launched, a door covering the front of the telescope protects delicate optical elements of the telescope. Shortly after the instrument is in orbit, the door is opened and remains open permanently. X-rays from the Sun enter the telescope through narrow slits of the Sun's shield. Filters over these slits allow only X-rays to enter the telescope. The X-rays are reflected by the mirror's inner surface to form the image. It is similar to the way a lens forms an image in an ordinary camera. The X-rays traveling through the telescope tube are focused by a mechanism which adjusts the distance between the mirror and the image-forming CCD. A shutter controls exposure time. The X-rays then pass through additional filters in order to select the particular portion of the X-rays that will be used to form the image. To make a visible light image of the Sun, the telescope uses the visible light optic. A glass filter blocks X-rays from interfering with the visible light image. When this video ends, you can get more information by clicking on each labeled part.
The reason this is closed is during launch we want to make sure everything's kept as clean as possible. We don't want to just launch it with this configuration, because what will happen is dirt, dust, and whatnot during launch, during your vibration loads, are going to start collecting on this surface, and they could get on the optic, and what happens is that'll mess with your resolution on the CCD. Good.
All set. When the telescope is in orbit and the front door is opened, the sun shield is in place to reflect the heating rays of the Sun and thereby helps to maintain the required internal temperature of the X-ray telescope.
This is the visible light optic, which we assembled last week. You can see there's optics in there. The little red pads are for a blue band or G band filter, and also a neutral density filter, because this looks directly at the Sun, and the Sun's so bright we have to remove about 99.99% of the Sun.
And it works sort of like this. It has a section which is, and typically we make them out of glass, although they have been made out of metal, but glass gives better results. A section which is a paraboloid. And in order to make a practical telescope, we need to shorten that distance. So we also put another piece of glass behind where this is a hyperboloid, or hyperbola of revolution, which shortens the focal length further. So an X-ray would come in, hit here, hit here, hit here, and be reflected to the focus.
This optic consists of a primary mirror, which is the top section here, separated by a gap, and then we have the secondary down below. And what happens is that light, I should explain to you that the reason that this is a grazing incidence mirror is that X-rays can go right through normal glass. So if you had what you think of as a normal lens where you try to refract the light to a focus, the X-rays would go right through the glass and not be affected by the material at all. So the only way to get them to focus where you want them to is to have them graze off the surface, sort of a glancing blow, and come to a focus where the camera will be. So the first optic they hit here is the primary mirror. It's at about 0.9 degree angle, so that's the grazing incidence. Then the rays hit the secondary mirror, which is about 3 times that angle, or 2.7 degrees, and come to a focus.
These X-rays will actually be reflected off the surface almost like a stone skipping off of water, instead of just going into the water. If you throw a stone directly at the water, it goes into the water. But if you throw it at a shallow angle, flat stone will actually hit the water and bounce off. And that's sort of what's happening with these X-rays.
Straight up. And you just want to make sure you rest straight down?
Yeah. All right, it's on.
Hang on.
Okay. You ready? I'm ready. We're picking the optic up. It's only $2 million lens, so the people know. I'm feeling faint. No, I'm teasing you.
Okay, just faint after you put it down.
I'm gonna be looking kind of in this direction, and you look in this direction as we guide the mirror in.
Okay.
All right.
You just guide it. Okay? I'm gonna let you get on. You're on?
Yep.
We gotta rotate it to there. Papers that can come out.
Yeah, the papers can come out
Everything's out? We're on, both pins. Len, we're in.
now. Okay, so we need
Oh,
a.
I'm there, nice and smooth, Peter. That was my biggest concern.
Yeah, mine too.
These. Len, can you see okay? This cable we can do even tomorrow if you.
All right, well, this is
So what model is this now?
the mass and both the structural and the thermal model. So we built it identically to Solar B.
Camera in?
Yeah, that's the camera in. On the inside, this is where obviously where the mirror goes, is up front, and but as you can see, attached both rear and up front where I am are some of the thermal controllers for keeping the tube warm. We allowed the center of the tube to get cold, or to get as cold as it would get with the front and the rear hot, but because there's really nothing in there. But the front and the rear of the tube is where the components that we were concerned about their temperature. So glued to the inside of the tube are the heater controllers and the heaters themselves.
This is the rear of the telescope. So this surface right here is the interface plane with the camera. The Japanese provided the camera, and that would fit here. This right here is an access port for during the period of actually construction. So you can close this up, you can get in here. And in particular, this lived right over the top of the focus mechanism. There's also this feed through here, and what we would have is all the wiring on the inside came to feed through connections. And so the cables came up on the spacecraft from here to the bottom of the box, and then they came out of the box to the various places that they had to go with these cables. And then running underneath and around those covered cables are these open braids, which are to take care of the grounding, so you don't get very high charges and get sparking that kills your electronics. Now, right here in the center is the main tie-down point to the spacecraft, and we've stiffened up the center of this tube quite a bit so that all the forces that this was supposed to get during launch can be controlled and held without damaging the tube. As it turned out, the forces that we were expected to have here were much higher than the actual forces. So when this was designed, we were designing for almost 50 Gs, but in the end, we had something, more like 10 or 12. Running further forward, we get to another mounting point right here, which I believe that this sat right at the forward end of the spacecraft deck. So I think the distance between the forward and the rear end of the spacecraft deck is from this tie point to the front tie point. So that gave us some baseline to tie this down on. This is actually a no-no, having a distributed mount like this in a telescope, because as the spacecraft bends, it actually bends your telescope. And we could get away with it in this system because we had only that single mirror up front. So we have another feed through here, and this was another opening that we could get in and make connections to the back side of the mirror and things like that. But then once it was closed out, it acted as a location to get air out of the telescope as the telescope was going up. So this right here is actually a vent. The air comes through here through a very tortuous path that allows the air to come out, but no light to get in. It actually suppresses light so that it allows 1 part in 10 to the 12th of light to get in. So it's very, very black. In fact, we tested how much light could get through this the same way we tested how much light could get through the filters. The mirror system mounts right to here. The door bolts on somewhere, and I'm not seeing its bolt-on point. Oh yeah, right here. So the mechanism for bolting on the door is right here. This Velcro is for supporting the blanket. So when the blanket was wrapped around, it was held down with the Velcro and then taped on. And then finally we have this cube, which is really the only piece of optics left on it. This is a very precise cube that's used to reference the actual line of sight of the telescope. So once we built the whole thing, we figured out where the line of sight of the telescope was, then we mounted the cube on there so that it was aligned as close to the line of sight as we could get it, but then we figured out what the deviation was. And ultimately, when the flight telescope was mounted on the spacecraft, we used this cube to align the telescope to the spacecraft. Let's put this one inside.
As far as the thermal protection is concerned, the blanket is quite useful feature to prevent from heat loss and vice versa from heat from coming back in. But we also have other ways to provide thermal protection is to give a surface property finish or thermal coating. For example, in our front door has relatively low absorptivity in the solar range to minimize sun being absorbed. Our instrument needs to be maintained at a fairly constant temperature around room temperature, namely about 20 degrees Celsius. So we actually have heaters that are mounted on the tubes of the telescope, and we have finite amount of heater power that is available. So in order to maintain the heat internal to the telescope, we actually applied what's called the multi-layer installation. It's actually also called a thermal blanket. The major bulk of the blankets are made of aluminized mylar. They're a 1/4 mil thick, and in our case we have 18 layers. They are separated by background mesh to keep the individual metal layers separated from each other. And what it does is actually it reduces total emittance through the blanket by having that metallization layer. The edges of the blanket, after it's been trimmed, are typically taped to prevent from the inner layers from being exposed to the outside. But in order to vent the trapped air internal to the blanket, we have vent assemblies. They are typically micro-meshed and is small enough to let the air out, but any contaminants, potential contaminants that might be trapped in there doesn't come through. And the outer layer is, once again, is 3 mil aluminized Kapton, and Kapton side is exposed. That's why you see the kind of the gold finish that appears to on the outside. From the midsection? Yeah, so it's like that. Go, keep going, keep going. Like that.
So go this way also. Over this? Is that right? Or is that the bottom?
No, that's the
Yeah,
bottom.
that's the bottom.
Yeah.
Like this. Go on over further, huh? All the way around.
And before we do that, what we should do is close it. The outer jacket, which is the black part, is the only thing that will be visible from the outside of the telescope.
After we delivered Solar Bee to the spacecraft people in Japan, it was integrated onto the spacecraft, and they were doing environmental testing of the whole thing. And part of this testing involved running us to very cold temperatures, what we call cold survival temperatures, which is around minus 30 degrees centigrade. And at that temperature, we're not supposed to operate, but we have heaters on board to maintain the temperature. The problem we encountered is when we tried to turn on the operational heaters while the whole spacecraft was still cold, we had a circuit breaker that tripped. We're able to work our way through it, but it's not the way it's supposed to work. It counted as a failure of the test, and of course it's a failure for us in the sense that if we were in space, we might not be able to do these operational workarounds to make things come on, in which case we could find ourselves essentially dead in the water. So it's something that had to be repaired. The plan, basically, after discussions between ourselves, NASA, and the Japanese satellite people, was to change that resistor out. Now, in order to do so, we had to fly some people to Japan. We removed the circuit board that carries that circuit breaker, which is the power supply for our instrument, and brought it back here to work on.
All right, Florine, have you come up with that way to attach the one ground to the other?
I was making those jumpers, and then he said he found the board, so I was coming to see if you still needed those
Yeah,
jumpers.
I'm still in the same boat. I need a way to have this ground plane connect to the ground plane of the real board.
Okay, I'll be right back.
Okay.
Okay, so the Australians. Oh, the resistor's already out.
Huh?
Yeah. Oh, I didn't know that.
That the resistor was
I didn't know you guys took the resistor out already.
Oh, yeah. Right over there.
Oh, this one here? It's already pulled out?
Right over here.
Okay.
72.
There's a little bit of, looks like fibers in one hole on one side, on the top side. If you tilt the board up this way and look down into the hole, there's looks like about 4 fibers. Look like fiberglass, but it's white. I don't know what. And it could be.
It might be from the
it could be
cotton
from
soil.
the. Yeah,
Yes.
I bet that's what it is. I bet it's
Yeah.
cotton.
Yeah, we can
But
pull
it's
it
down
off
in the
again.
hole
Yeah.
a little bit.
Yeah, I'll clean it off. Training it again.
You have a pedal or a button that you push to
Yes.
start the start. Got you. Did you have to apply any flux to start the fire?
A little bit. Yeah, so I get even heat in it.
Should ask for your own trailer with a star on the door floor.
Yeah.
Probably something she's done hundreds of times, but.
Okay, I'm gonna have our own inspection people take a peek.
Right,
So,
Get out of there. You're holding up progress.
no, I'm not.
Yes, you are. Me.
I'm holding you up.
That's right, I'm progress. Because if I put an R on there,
An R, it's just.
what? What?
We've survived.
Get him his own paperwork if you're gonna put an R on him. Oh, no, I'm gonna put it on that one. He's drooling on it, he has no beard cover. He, what else?
You don't have a beard cover either, what are you talking
Well, I'm not sitting on top of it. Shame on you. It's not all the way out, you can see a dent. Yeah, but you can't see the bottom of the dent, it's like a concave. Doesn't matter. Chucky. Needs to flow, sweetie.
These usually not have any of the details about these things. Sorry.
And this guy is going to have like all these.
Good to go.
Good to argue with them. You gotta rebuild the building. No, we have to do that.
Oh, I remember
Because
that.
that,
Looks
if you look
better.
at anything backwards,
Ta-da! All done.
It's a minus 33. All right, so now we'll start turning it up. 50, 100, 50, 200, 210, something like that. It will, but I mean that's generated by the pulse box, so it's not something that...
Oh, okay, so that's something you don't know what it's supposed to be.
Right, right. That's just verifying it.
You got, what position is the switch in up there?
Oh, good point.
Is
Switch
it off
isn't on.
position?
It's in the off position.
Off position.
Okay, you got a paycheck this week.
Well, that's the next step.
And it tripped. Hold on.
There is.
1.95.
1.95. You
Yeah.
done?
I'm done.
All right.
No, I'm sorry, 1.93.
He lied.
1931. I saw it
Ah.
right there.
Thank you. I would tell which is inside out on these things.
Don't worry about it, as long as it goes on your head.
Right. when knighthood was in flower or something like that, right? Don't see any burn marks.
It's a little cold.
It's a little cold. You want to leave it
A little cold.
I could set it out on the flow bench for a couple of minutes. It'll probably come up pretty quick.
No.
That was worth staying here all day for, wasn't it? Yeah, I'm sure you got a little bit more imagination than that, right?
Done deal. I'm going home.
They did a fine job.
They did well. They did a good job. What's the problem?
You want to sit down and discuss?
Discuss what?
What do you need to discuss?
Well, why don't we do that later? That's not, we have to do that now.
We're going to, when we put the change adjustment.
Does this have to be done now? Do we have to have this discussion now?
I don't understand the issue, but our understanding is that this is a final adjustment, and then afterward you will put alignment beam.
No.
That's understanding yesterday.
No, the align. We're not going to drill and pin this now. We're going to drill and pin this after we get the after we get the mirror.
Okay.
Yeah, this is.
Okay, that understand.
Yeah.
That's, I think I understand.
Yeah.
Yesterday, yes.
Right.
So, but you plan to change something here?
We may have to change this piece right here. This piece right here may get changed if the mirror's got a very short focal length. This may have to be changed. This piece, the middle piece.
Which one? Lower one?
This one right here.
Okay.
And if it's very short, then we may have to change this piece here.
Okay. So depending on the middle length, you may have to do something.
Yes,
to this.
absolutely. We understood that. Because we only have a total of 5. See, there's only a total of 5 millimeters of total change right now, because you can take out this spacer here, and then you get about 2 millimeters of change here. And then after that, you can carve some of the space of here off until this almost meets our piece. And then this has to be cut back, and these screws have to be moved a little bit.
Do you have a good constraint on the middle length, focal length now, or you don't have any information at this point?
None.
No.
None.
So you have to measure that.
Right. We have to measure that. That's going to be done when we get the mirror in a couple of months.
So you are not changing what you have been saying at all.
Right.
Okay.
Yeah.
So they feel what you are saying is different from what you said yesterday. So there is a misunderstanding.
Yeah, must be, because I haven't changed anything.
Okay.
Yeah. There's not going to be any final connection today. There's not going to be any final connection before we go to Goddard.
The purpose of today's activity is to practice.
Is to practice and to set it up so that, and then what'll happen is we'll tighten these screws up here. And that's it. We won't even put the adhesive in. But even if we put the adhesive in, we can still take it apart, take it off the camera, bake the adhesive out.
So there is a possibility that we don't need to change anything, just adjust,
right.
depending on the mirror length.
Exactly.
何も言ってることは違わないと。キロと強で。キロと強で言ってることは全く。
Yeah, well, if we have to modify it, then these screws would be moved back this direction a little bit, and this piece would be cut off here. This part right there. This part here would be cut off. So it would be moved back here a little bit. This screw would move up to here, this screw would move up to here, we'd cut this piece off, this would move up a little bit, this would move back a little bit. That's all we would do. And then these screws would be moved up here a little bit. Why don't we do that all now? Why don't we go have the discussion now?
Okay.
All right. All right.
Do you want me to come out?
Yeah, everybody out, because we're not going to do this till after lunch.
Sorry, we're taking a 15-minute breather.
Then we will go and take these drawings and we will put together and show you exactly how to make it as small as we can possibly make it.
Okay. But right now, keep in mind that our current adjustment capability is twice the requirement we placed on Goodrich. So we have 100% margin.
And all that pinning's going to be the right-hand one, we would actually add a little material to the middle piece.
This is with the 3mm aluminum spacer?
This is removing the 3mm aluminum spacer and still adapting for a 15mm Delrin spacer. So if the mirror turned out to have a focal length that was 5mm longer than nominal, we would be in the situation shown on the right. So in order to meet that situation, we would have to make a new middle piece that's slightly longer. This piece here we would add a little bit of meat, a little bit of metal in the middle.
What is the reason to remove the existing 3mm aluminum spacer?
We never wanted to fly a spacer there. That spacer is only in there for the Goddard test, with the condition in which the mirror is 5 mils shorter than nominal. In order to do that, then we have to remake the middle piece, and we have to remake the piece that will ultimately be attached to the camera. And what you see is we are 6.5 millimeters shorter than nominal, with a 0.5 millimeter of adjustment range. So that means we got a total of 7 millimeters shorter than we are at present. So the 7 millimeters plus the 3mm shim is the 10 millimeters that we need to save.
I thought it was just a continuous gas leak. It just never cut it. And then finally I saw it's an angle. Yeah.
So we built it this way because we thought this would be right. If it turns out not to be right, we knew we were going to have to remake this. But we thought this was right. Fine. All right, let's suit up. The decisions we are going to make here are going to make or break all our careers, okay? I'm serious, okay? Okay, and I will not move forward unless I have actual signatures on this one, okay? We have plus or minus 1 millimeter of focus range. Now we're gonna have to, this is hard, we're gonna have to work this out. It's gonna take a lot of drawings, because I have no idea about the sign. So if you're confused, that's because I have no idea, all right? So if we take the focus range that we have available to us, and we have in our calculation of actual focal position, we got a roughly 175 microns of error on each end, right? So if you take your focus range, just chop 175 microns off either end, essentially, right? It's gone. Wherever we set up in the middle, we're going to need 175 microns of buffer at either end, right? Is everybody with me there? Okay. Then we've got issues related to how we made our measurements here versus how we're actually going to operate the instrument. The tube is going to dry out. It will get shorter. The temperature will be different. And therefore, there is a set of errors that are here. Either they're errors or we calculate them, whatever it is. These are real changes in length. See, the problem is you know what CME is, right? We know what the coefficient of moisture is, right? But what we don't know is the relationship between the moisture in the air and the moisture in the tube at the time it comes to equilibrium. That's what we don't know.
No, but he's asking if it was 100% humidity.
That's
within
fine.
a million
That's
years.
CME is not.
If it was as saturated as it could possibly get, and then in orbit it's as dry as it can possibly get.
We don't know the first answer.
If I had 100% humidity, right, and it came to equilibrium with the tube, I don't know how much what the percent humidity in the tube is, and therefore I don't know the number to multiply times CME to know how much it grew. All right. I will hold that still. All right, go to negative 1500 and say when you're about to go. Is it done? All right, so negative means you're moving that way here. When this pulls this way, it moves the CCD the other direction. So negative means you increase the distance between the mirror and the CCD. So you increase focus length. So you pull this way, but in the camera you've got a wedge. You've got a lever. So by pulling it that way, the CCD goes this way. So negative increases focal length. So
write that down somewhere?
yeah. Yeah, so mark that, negative. Add 2 eds. Negative increases focal length. Increases focal length. Plus is minus.
This is where it gets scary, because everything's vulnerable now. I'm going to verify. Serial number 2's going in. Let me do this. Where's 2? Filter wheel 2 cable out of the way once you stake it.
Yeah.
And then I'll install this in.
So with this guy, I dab it?
Yeah. You take a little and dab. That's it. And just dab and dab. That's good. Okay. You pull that back. There it goes. Oh. No, it should stay. But it's just, thank God it's in.
Motion or not?
Okay, let me do it.
Well, I didn't write it.
All right, you need to rotate a little bit.
Yep.
Is that going to clear?
Yep. Just barely, but it's gonna clear.
You sure?
Yeah, we got about.
All right. Oh. Yeah, you're on the bottom pin. I don't know how. I can't see how far. Not the less than the thickness of the flange. All right. Okay. Now you're kind of at the beginning of the.
Which way does the slap go, up and down?
Yeah, it goes up and down. How are we doing on top? So you have to raise. You have to raise it the width of the slot.
Oh,
There.
good. Oh,
There.
good. Good.
There we go. All right.
Excellent. Yeah.
All right. Wait. Yeah. All right. He's got to.
Okay.
He's got. Wait. Drive the bottom forward.
Clear.
No.
No,
You sure?
Yeah. We got about.
Is this in? No, he was right. Yeah.
Oh, okay, yeah.
Yeah. Moscow. All right. Is this still on here?
Yes, yes.
Okay. All right. All right. Keep going. All right. I can get this screw in over here, but.
I have two in them. I think you get one more.
Yeah, I got one in on the bottom here.
All right.
All right. How do we get this thing out of here?
We have to drop it down
Oh, okay.
and then rotate it out.
Okay.
In the ass.
All right. All right. So we'll do that, and then we'll get the handles off.
Yeah.
Then we can push it in because right now the vent is right in the way. Okay. The vent comes line to line against it. The purge fitting. Yeah. Well, maybe that's the last time.
I got a picture.
That's good. That's what I wanted. Yeah, you got a picture of Tyler taking a picture.